talking about solving problems given correlated instances.
Okay. Well, thanks for sticking around. I'll try to make this quick. All right, I am Dheeraj. This is joint work with Shafi, also at MIT. I'm talking about solving problems in P given correlated instances. So let's think about problems in nature. Often we end up having not one instance in isolation, but many instances which end up having correlations. So we see this in, say, DNA sequence alignment problems, or we have a number of sequences from a bunch of species which are correlated. And so the idea is it might be possible to use these correlations to get speed-ups over when you don't have these correlations. So let's look at some examples of what's been done with correlations before. So you have a number which you want to find its factorization. So ordinarily, we believe this is hard, that you shouldn't be able to do this efficiently. But if you're given another number which is correlated in a given way, specifically that it has one of the primes in common, you can find the factorization efficiently by computing the GCD of the two things. And so this is actually used to break RSA in certain cases due to bad choices of primes. And so also, it's been shown that for constraint satisfaction problems, to find an approximate solution for a random CSP with correlated instances, you can also do efficiently. So what we'll be looking at now is we're going to be looking at polynomial times problems, specifically sort of the things that you look at in fine-grained complexity framework. And we'll look at how correlated instances can help us with that. So now, how are we going to model this idea of having correlated instances? We're going to think of these correlated instances as coming from some sort of generating process. So what that means is, first we'll generate a primary instance, which is the instance that we want to solve. And it's going to have some primary distribution, and it's going to have some solution S, and that this solution is going to be important. And then we also generate auxiliary instances which have other solutions which are hidden. And these solutions depend on both the solution to the original primary instance and the primary instance. So now the question is, what sorts of correlations do we want? So now we're looking at a number of properties that we want for correlations. We want a non-trivial speedup. So we want to not be able to generate these correlated instances from the original instance, because this would imply speedups for the original problem. And we also want a non-trivial improvement. So if we have too many correlated instances, it might be too easy to just read off the solution from the correlated instances specifically. And in addition, we want the solution to not be derivable from an auxiliary instance by itself. Say you can't just have the auxiliary instance be, say, the solution to the primary instance. That gives us things. And lastly, probably the most important criterion and the hardest criterion to define is the idea that the model we should be looking at should in some sense reflect some sort of real world application. So now let's kind of compare and contrast correlated instances to some other things. So correlated instances are different from average case analysis because our distributions can be worst case. Our primary distribution can be worst case. And also, sort of in smooth analysis, what you're doing is you're perturbing a single instance of a worst case solution, but here you're given multiple instances. And it's different from amortized analysis in that you only want to find the solution to your primary instance. not all of the instances. So now, which problems should we consider? So we want problems where there are barriers to beating the worst case solution and places where we think we can find improvements with these correlated instances. So in particular, we'll be looking at longest common subsequence, edit distance, and dynamic time warping distance, all of which have essentially optimal algorithms assuming strong exponential time hypothesis. So specifically, we'll look at longest common subsequence, which, as you can recall, is the longest non-consecutive substring that appears in both strings. And so we look at the longest common subsequence of these two strings. It's pretty easy to see it's that. And we also look at a generalization where we consider the solution is a set of pairs and a number, which is sort of the value of this set of pairs. And we want to say we want problems where this value is only determined by the size of the set of pairs in some sense. And you'll see why this is important later on. So again, these problems can be solved in time n squared and with dynamic programming. They're hard to do faster. And also, sort of longest common subsequence has natural applications in the area of DNA sequence alignment. And so now the question becomes, can we take advantage of correlated instances to solve these problems faster? So first, we're going to have to define a specific correlation model that we'll look at. And so what this is going to be is, our primary instance is going to be it can be anything. It's a worst case instance of longest common subsequence, which has some solution. And so the way we generate the auxiliary instances is we take our primary instance and we take the solution of the primary instance, we draw random strings conditioned on the positions of the longest common subsequence of the primary instance being matching positions in the auxiliary instance. Now, if we look, we can see that the values of the string at those positions can be different, but we want the positions to be the same. So specifically, locations 2, 3, 4, and 5 in the first string match up with locations 1, 2, 3, and 6 in the second string. So also, we can look at this relaxed correlation model where instead of, remember, if we go back, we have these positions are exactly the same, exact matching. We can make them matching with, say, some higher probability than the two random characters. So here we can replace 1/2 plus epsilon with anything that's better than the probability that just you have two random characters matching. And we can also get subquadratic algorithms here with log n correlated instances. So our results are, with a logarithmic number of correlated instances, we can compute this in n log n when we have this exact model, and still in subquadratic time with the relaxed model. And this also generalizes to the pair-based similarity measures, where the dependence is on the size of the sets of matching pairs. So now, how do we do this? So first, we look at a pair of extended strings where each character in an extended string is a vector of characters in the original strings. And the way you do this is you take the characters from in the same positions from the primary instance and each auxiliary instances. You can see that in green here, and that becomes a character in the extended string. And similarly for the second string in brown, you can see that as well. So these are the two extended strings. And now what you do is you can just look for matches in the two extended strings. So now we see that the positions of the longest common subsequence in the original string will correspond to matching pairs in the extended strings. And this is not a coincidence. Because what happens is, if you have a pair of characters, one from each string, and they don't match, then the probability that in an auxiliary instance they're the same is going to be a half. But if they do match, it's going to happen with probability 1. So that means that with high probability, the set of matching pairs in the strings is going to be just the locations of the longest common subsequence. So now we just have to find all these matching pairs. So we can do this pretty straightforwardly with hashing. You can construct a hash table with the vectors in extended x, and then ask for each vector in extended y whether it appears in extended x. And you can see that this runs in time n log n, because sort of you have log n vectors and each hashing, or log n size vectors, and each hashing operation takes log n time then. And so what happens in the case of the relaxed correlation model? Well, now we don't have this exact match guarantee. We only know that these pairs are going to match with higher probability. But what ends up happening is that the pairs that we get are going to be closer together than just two random strings. And so we can use Hamming nearest neighbor search to find this. And it's well known that Hamming nearest neighbor search can be done in subquadratic time. So again, we have this hash table with vectors in extended x, or, well, it's not really a hash table anymore. And so we can use that to find the pairs of vectors to correspond to locations of the longest common sequence. And again, with a higher probability, this time due to Chernoff bound, you can show that with high probability, every string that's close, every pair that's close in Hamming distance will be part of the longest common subsequence. And that's exactly what I said here. So now we'll look at what's open. So the question is, can we find an example in nature where these correlations give us speedups? In addition, can we extend these results to other problems with polynomial time hardness? There's a whole array of problems that we haven't looked at. And also, is log n correlated instances optimal here? That's a question that we don't know. And another area that seems interesting is whether we get different results if we want to ask for an approximate solution rather than an exact solution. So what are the main takeaways from this presentation? So the main idea is, with these correlated instances, we can find these solutions faster than the worst case. And these algorithms look different than previous approaches to this problem. So now the question becomes, how do we model correlations and take advantage of them when they exist? Because correlations are common in the real world. The question is, how do you exploit them? Okay. All right, questions?
Thanks again.